Welcome to another deep dive from the Rooster Pod log. Today we're venturing inside the fascinating world of Apache Spark. We're going to see how it manages truly massive amounts of data. Think of it maybe like taking a tour of an enormous Lego factory and really understanding exactly how all those billions of little plastic bricks get sorted, moved, and assembled, especially when things get a little, well, chaotic.
Exactly. Yeah, you shared some really insightful stuff about what makes Spark performance tick or sometimes, not tick so well. We're going to be looking closely at concepts like data skew, what happens when Spark runs out of mental workspace, we'll call that memory pressure,
Okay.
and where the extra Legos go when the workbench is full, that's disk spill,
Right, the overflow.
and how Spark rearranges its building blocks, its data, using techniques like repartitioning and coalescing. Our mission today is to make these often complex ideas really crystal clear and immediately relevant for you. Whether you're a seasoned data engineer wrestling with a sluggish Spark job or, simply curious about the magic behind big data processing. And as you can probably tell, we'll be using this Lego factory analogy throughout to, well, keep things grounded and easy to visualize.
Okay, let's dive straight in then. Our first challenge, data skew. Imagine our Lego factory gets this massive shipment of bricks. Sorting them by colors seems straightforward enough, right? But what if, like, 90% of those bricks are red?
That's pretty much the heart of data skew. It happens when certain colors of your data, we call these keys in Spark, are far, far more common than others. Now, when Spark needs to shuffle these data bricks around, say during operations like joining different sets of bricks or counting how many of each color we have, that's called aggregation, it uses a default method to decide which bin each brick goes into. This is typically done using something called a hash partitioner.
Okay, a hash partitioner. So how does this actually work in our Lego world? How does it sort the bricks?
Think of it as a simple rule. For deciding which numbered bin each Lego brick, each data point should go into based on its color code, essentially. For every brick, Spark takes its unique identifier. The key performs a calculation. Technically, it gets a numerical code for that key, a hash code,
Okay.
and then it divides that number by the total number of bins we have, and it looks at the remainder. That remainder tells Spark exactly which bin that brick should be placed in. The formula is basically target partition, key.hashcode, percent unpartitions.
Okay, I think I get the sorting rule.
Yeah.
So back to our red brick problem, the overwhelming pile of red.
Right. If red is the dominant color, the skewed key, then the result of that hash code calculation, it's often going to point to the same few bins, no matter how many bins we have in total. So you end up with one or maybe a few bins just absolutely overflowing with red bricks, while the other bins have a much more balanced mix of colors. And this uneven distribution of work, well, that's where the problems start.
And what kind of trouble does this overloaded bin cause in our real Spark jobs? What's the impact?
Oh, it can be huge. This can turn what should be an hour-long job into a multi-hour ordeal. It costs significant time, significant resources. The executive think of this as the dedicated robot in our Lego factory, assigned to process the bricks in a particular bin.
Right, the worker for that bin.
Yeah, the one responsible for that overloaded partition is going to be completely swamped with work. It will take much, much longer to process all those red bricks compared to the robots handling the more balanced bins. This leads directly to what we call straggler tasks. These are tasks that run significantly longer than others in the same processing stage.
Ah, so the whole job gets held up just waiting for these slowpokes.
Exactly. The entire Spark job has to wait for these stragglers to finish their massive pile of red bricks, even if hundreds of other tasks finished ages ago with their smaller, more diverse collections. This just drastically increases the overall processing time. It can really, really hurt the efficiency of your data pipelines.
Okay, so it's a major bottleneck. How can we even tell if we have this overloaded bin situation happening? How do we spot skew in our Spark jobs?
The Spark UI is your best friend here. It's like the control panel for the Lego factory, right? It's a web interface where you monitor your Spark application. You can dive into the details of each processing stage and look at the task metrics. Things like how long each task took to complete, how much data it read as input, how much shuffled data it read or wrote.
Right.
If you consistently see a few tasks with drastically longer durations or maybe much larger input or shuffle read-write sizes compared to the vast majority of other tasks in that stage, that's a very, very strong sign you have data skew. Those tasks are the ones dealing with the overloaded partitions.
And you mentioned some actual code snippets we could use to see this data imbalance more directly, right? So we're not just relying on checking the UI after the fact.
Exactly, yeah. You can be proactive. You can examine the distribution of your data's colors, the keys, even before or maybe after a shuffle operation. The first one's pretty straightforward. If you have a data frame, let's call it DFF, and you suspect a column, say producted, might be skewed, you can just run df.groupbyproducted.count.
Right, just count how many of each product ID there are.
Exactly. This gives you a new data frame showing each unique product ID and its count. Then you can use something like keycounts.orderby, colcount.deci.show10. That just displays the top 10 most frequent product IDs and their counts. It'll immediately highlight if any particular IDs appear hundreds, maybe thousands of times more often than others. Confirms the skew right there.
That makes total sense, just seeing the raw counts for the most frequent colors.
Yeah.
But the other code snippet you shared seemed a bit different, more about the overall spread.
Yeah, that's right. The other approach uses approximate percentiles. The code looks something like keycounts.selectexperto, percentile 0.5, percentile approx count 0.9, max count.show.
Okay, what does that tell us?
So percentile somewhere count to 0.5 gives you the median count. Half your product IDs have this count or less. Percentile approx count 0.9 gives you the 90th percentile, meaning 90% of your product IDs appear with this count or less. And max count just shows the count of the single most frequent product ID.
Ah, I see.
By comparing these values, especially how much higher the maximum count is compared to, say, the 90th percentile, you get a really good feel for whether the top few keys are just way out of proportion. It's another clear sign of significant data skew.
Got it. Okay, so we've identified our overloaded Lego bin. Now, what happens when the builder's workbench itself gets too crowded? Let's talk memory pressure when our Lego factory floor just can't hold all the bricks and projects at once.
Ah, yes, memory pressure. Good one. In our Lego factory, imagine the main assembly tables are just overflowing with bricks, half-finished models.
Chaos.
Pretty much. In Spark, this happens when the memory being used by the individual workers, we call them executors, remember, independent processes running tasks. Or sometimes even the main coordinator, the driver node, when the memory they're using exceeds the amount that's actually been allocated to them. Now, Spark's actually got this pretty clever way it handles memory on the executors. It's called the Unified Memory Manager.
Unified Memory Manager. Okay.
Basically, it splits the available memory up into a few different key areas.
That's laid on us. What are these different compartments?
Broadly speaking, you've got execution memory. This is where the intermediate data lives during active processing, things like shuffling bricks between tables, sorting them, doing aggregations. It's really where the actual building happens.
Okay, the active workspace.
Exactly. Then there's storage memory. This is used for caching data, basically, keeping frequently accessed data right there in memory if you explicitly tell Spark to, persist, like keeping your most popular Lego instruction manuals super handy.
Makes sense.
We also have user memory, which is for your own code's objects and Spark's internal bookkeeping. And then there's a small slice of reserved memory, just for the underlying system stuff to operate smoothly.
So if execution memory is the assembly area, storage memory is like a handy shelf for popular parts or subassemblies you've already built.
Perfect analogy. And what's really clever is that the boundary between execution and storage memory is flexible. It's not a hard wall. There are configuration settings like spark.memory.fraction and spark.memory.storage_fraction that define the total memory Spark can manage and the initial suggested split between these two. Think of it like sections of the factory floor adapting based on whether you need more assembly space or more storage space right now.
Flexible how? So the assembly area can borrow space from the storage shelves and vice versa.
Precisely. If the assembly area execution memory needs more space, maybe to sort a particularly large batch of bricks, it can borrow from the storage shelves from storage memory. Of course, that might mean it has to temporarily put some of those pre-assembled parts back into less accessible storage. In Spark terms, that means evicting some cache data from memory. And similarly, if the storage area needs more room to cache more data, it can borrow from the assembly area, but only if that space isn't currently being actively used by a running task. There are limits, though. They can't just endlessly steal from each other. That would hurt performance, too, right?
Right. Okay, so what kinds of things in Spark actually lead to this memory workbench getting too crowded?
Yeah.
What causes this memory pressure?
Several things, really. If your Lego bricks themselves, your data records are very large or complex when they're unpacked, deserialized. Those objects can take up a lot of space in memory. When Spark shuffles data moving those bricks between assembly tables, the intermediate blocks of data being transferred can also be huge and eat up a lot of memory.
Right.
If you're doing complex aggregations, the temporary storage areas where Spark keeps track of intermediate results like sums or lists can grow unexpectedly large. And of course, the most straightforward reason is just you didn't give the workers enough memory to begin with, not enough spark.executor.memory allocated for the job you're asking them to do.
That seems obvious when you put it that way.
Yeah, and a surprisingly common pitfall is trying to bring a massive amount of processed data back to the main coordinator, the driver node, using a .collect operation. The driver has its own memory limits set by spark.driver.memory, and it can easily get overwhelmed if you try to pull back like billions of Lego bricks worth of results all at once.
Right, trying to fit the whole factory's output onto the manager's desk.
Yeah.
And when this workbench gets too messy, you mentioned garbage collection, GC. What's that all about in our Lego factory?
GC. Think of garbage collection as the factory floor manager suddenly yelling, "Everyone stop working! We need to clear out all the unused parts and empty bins to make some space."
Uh-huh. Okay, a forced cleanup.
Exactly. In Spark, GC is a process where the Java virtual machine, the JVM, which Spark runs on, tries to reclaim memory that's no longer being actively used by your application. But here's the kicker. When GC runs, all the Spark tasks on that specific worker, that executor, are temporarily paused. These are often called stop-the-world pauses.
Ouch, so work just stops.
Work just stops. And these pauses can significantly slow down your overall job. If memory pressure is severe, if that workbench is constantly overflowing, GC might happen really frequently and take a long time each time. Your Spark job just crawls along. Frequent and long GC pauses are a huge red flag. They're a telltale sign your executors are struggling with memory, and it seriously impacts how well your application can scale.
And if the manager can't find enough space, even after all that frantic cleaning, what happens then?
Well, that's when you run the risk of disk spill, which we'll get to next, or even worse, the dreaded out-of-memory error, or OOM. That's where the whole Spark process just crashes because it literally cannot get the memory it needs to continue. Game over for that worker.
Yikes. Okay, you also had some code examples of things that commonly cause memory pressure, like caching a huge data frame.
Yeah, exactly. If you use .persist, storage level .memory only, on a really large data frame, you're essentially telling Spark, keep this massive pile of assembled Lego models right here on the storage shelves, ready to go.
Sounds good for speed, maybe.
It can be, definitely, for speeding up later operations that reuse that data, but it can also very quickly fill up your available storage memory, and that might leave less space available for execution memory when later stages need it for shuffling or sorting, potentially leading to pressure and maybe spills down the line.
Right. Fills up the shelves, no room left on the workbench.
Precisely. Similarly, using memory-intensive window functions, like trying to rank all your Lego models within each color category using something like rank.over-window.partition-by color.order-by-size on a huge data set. That can require significant buffer space per task to keep track of all the rankings.
Okay.
And like we said before, just calling .collect on a massive data frame to bring everything back to the driver. That's a classic way to blow out the driver's memory.
So what's the factory manager supposed to do when the workbenches are overflowing? What are the immediate actions?
Tuning your Spark memory configuration is absolutely key here. You might need to give each worker a bigger workspace by increasing the spark.executor.memory setting, adjusting spark.memory.fraction, and spark.memory.storage fraction can also help fine-tune that balance between execution space and storage space.
Okay.
And sometimes, honestly, a more effective approach isn't just more memory, but giving each worker less data to handle at once. You can do that by reducing the size of your data partitions, often using repartitioning, which we'll definitely get to soon.
Okay, so we've seen what happens when the workbenches get too crowded. Now, what happens when things really get out of hand? When some of those Legos start falling off the tables and onto the floor, or in our Spark world, onto the hard drive? That sounds like disk spill.
You've got it. Disk spill is basically Spark's emergency valve. It's there to prevent those catastrophic out-of-memory errors when a worker, an executor, is under severe memory pressure, specifically within that execution memory area we talked about. When a task needs to allocate more memory, maybe for shuffle buffers, those temporary holding areas for bricks being moved, or for sorting, or for aggregation buffers, and it just can't get enough, even after trying to borrow from the storage shelves, it has to resort to writing some of the data it's working on to the local disk.
So it's literally taking some of the work in progress, like a half-built Lego castle, packing it up, and saving it onto the hard drive for later.
Exactly that. Spark serializes a portion of the data structure it's working on, turns it into a more compact format for storage, and writes it to temporary files on the executor's local disk. The location is usually set by the spark.local.dir configuration. Later, when it needs that data again to continue its work, it has to read it back from the disk and deserialize it, turn it back into a usable Lego structure back into memory.
That sounds incredibly slow. Like having to stop building, carefully pack some bricks into boxes under the workbench, and then later having to rummage through all those boxes to find the right pieces instead of having everything right there.
That's a perfect analogy. Yeah. There's a significant performance penalty. First, you have the overhead of serializing the data to disk, and then the cost of deserializing it when you read it back. But the biggest hit, by far, comes from the fundamental difference in speed between accessing data in RAM or Workbench and accessing data on disk, those boxes under the Workbench.
RAM is way faster.
Orders of magnitude faster. We're talking milliseconds for disk versus nanoseconds for RAM. So even a relatively small amount of disk spilling can drastically increase how long your tasks take, and therefore the overall processing time of your Spark stage. It really slows things down.
Is there a way to see if this under the workbench overflow is happening? Can we monitor disk spill?
Absolutely. The Spark UI tracks this diligently. If you look at the metrics for each individual task, you'll find a specific value called disk bytes spilled.
Okay, disk bytes spilled.
Yep, that metric tells you exactly how many bytes of data that particular task had to write to disk during its execution because it ran out of memory. This is also aggregated up to the stage level, so you can quickly see if a whole processing step in your Spark job is experiencing a lot of spilling across its tasks.
Gotcha. What kinds of Spark operations are most likely to cause this dreaded spilling? Which Lego building activities are riskiest?
Well, operations that involve shuffling large amounts of data across the network are prime candidates. Things like joins between really large data frames where data needs to be redistributed based on the join keys. Also, grouping your data by a key that has a very high number of unique values, high cardinality, we call it, especially if you're also trying to accumulate a lot of data within each group.
Like using collect list, maybe?
Exactly. Using something like collect list to gather all related Lego bricks together for a very popular key can easily blow out the memory for that task and lead to spills. And naturally, if you're trying to sort a data set that's significantly larger than the available execution memory for each task, spilling to disk is almost inevitable. Spark needs that temporary space on disk to perform the sort.
Okay, so if we're seeing a lot of disk bytes spilled in the Spark UI, what can we do? How do we stop the Legos from falling on the floor?
The strategies overlap a lot with what we discussed for general memory pressure, actually. The most common first step is often just giving the workers more RAM increase, spark.executor.memory. Give them more workbench space.
Makes sense.
Reducing the size of your data partitions can also help significantly, often using the repartition operation, which we'll discuss next, to create more smaller chunks of data. That means each task has less data to process in memory at any one time. Sometimes optimizing your data types helps using smaller integer types if you don't need the full range of a big one, for instance. Every byte saved counts when memory is tight. And occasionally, you might need to step back and rethink your approach entirely. Are there more memory-friendly Spark transformations or algorithms you could use to get the same result without needing so much intermediate memory?
Okay, good strategies. We've talked about what happens inside the factory when things get messy. Now let's talk about proactively rearranging those Lego bricks, maybe to prevent the mess. First up, the repartition operation.
Repartition. Yeah, think of this as initiating a major reorganization, like deciding to move all the Lego bricks across the entire factory into new specific bins. The repartition, num partitions, partition express operation in Spark, triggers what we call a full shuffle of your data. The goal is to create a new set of exactly the number of partitions you specify, num partitions. And optionally, you can provide specific columns or expressions, the partition express part that Spark should use to decide how to distribute the data into these new partitions.
A full shuffle, that sounds like a pretty significant undertaking.
Yeah.
What exactly happens under the hood when we tell Spark to repartition?
Oh, it is. It's a fairly involved process. First, the tasks in the Spark stage that come before the repartition call read all of their input data partitions. Then, for every single Lego brick, every data record they process, Spark needs to figure out which of the new target partitions this brick should belong to.
How does it decide?
Well, if you've provided specific columns as partitioning expressions, Spark takes the value of those columns for that record, calculates a hash of those values, and then uses that hash, usually with the modulo operator like before, to determine the target partition out of the total number you requested.
Okay, similar to the initial partitioning.
Very similar. If you don't provide any partitioning expressions, if you just say repartition 500, Spark typically uses a round-robin approach. It tries to distribute the records as evenly as possible across the new partitions, just assigning them one by one. But this method doesn't guarantee that data with the same key will end up in the same partition, which is often important.
Okay, so Spark figures out the new bin for each individual Lego brick. What happens next?
Right. So after the decision is made for each record, the records get serialized, converted into that compact, transportable format. Then they're buffered in memory on the executors that are doing this pre-repartition work. These buffered records are grouped together based on which new target partition they're destined for.
Uh-huh.
Once these buffers fill up, or maybe when the task finishes processing all its input, this buffered data gets written out to shuffle files on the local disk of the executor doing the writing. These shuffle files are organized so each file, or part of a file, contains data heading for a specific new target partition. And it's worth noting, if the executor is under memory pressure during this shuffle write phase, it might even have to spill these shuffle write buffers to its local disk too.
Wow, okay. So the data is now written out to these temporary shuffle files on the local disks of the original executors.
Yeah.
How does it get to its new repartitioned home?
This is where the network gets heavily involved. The executors that are going to be responsible for processing the new partitions in the next stage of your Spark job, they reach out across the network to all the executors that wrote those shuffle files.
Right?
They then request and fetch the specific blocks of data, the pieces of the shuffle files that contain the data destined for the partitions they are responsible for. Once they receive these blocks, and they might have to read them from disk if the sender had spilled, or if the receiver itself is under memory pressure and has to spill the incoming data.
More potential spilling.
Yeah. Then they deserialize the data back into usable in-memory objects, and only then can they actually proceed with whatever the next Spark transformation or action in your application is.
Man, that sounds like a tremendous amount of data movement.
Mhm.
Lots of potential overhead, reading from disk, writing to disk, sending potentially everything across the network.
Absolutely. Repartition is generally considered one of the most expensive operations in Spark, period, because it involves significant network I/O, potentially sending all your data between executors. Significant disk I/O, both the shuffle writes and reads, plus any spills. And significant CPU usage for all the hashing, serialization, deserialization.
Well,
It creates a very clear shuffle boundary in your Spark job's execution plan. You can often see it visualized in the Spark UI as a whole distinct stage dedicated just to this shuffle. Because it's so expensive, you should really use repartition judiciously. Only when you have a clear, compelling reason to redistribute your data like this.
okay, so when would we want to incur this cost? When is a full Lego relocation actually necessary beneficial?
There are a few key scenarios where it makes sense. One important one is to explicitly control the level of parallelism for the next stage in your Spark job. By setting num partitions to a value that's right for your cluster size and the workload, you can optimize resource use.
Okay, tuning parallelism.
Exactly. Another crucial use case is to break up data skew. If you've identified that partitioning by a certain key is leading to those overloaded bins and straggler tasks we talked about earlier,
Right.
you can use repartition, maybe with a different, less skewed key, or even just use the round-robin distribution, repartition n without a key, to spread the data more evenly before you hit that problematic operation, like a join or a big aggregation.
Using it to fix the skew problem.
Precisely. And finally, repartition is also really useful when you need to control the number of output files that get written when you save your process data, say to S3 or HDFS. By repartitioning to exactly, say, 100 partitions right before you write, you'll typically get 100 output files.
Okay, controlling output file count. Got it. You had some code examples for repartition, too, showing how to set a fixed number of partitions and partitioning by a column. Can you walk through those again quickly?
Sure. So if you have an input DF and you just want to ensure the next steps run with, say, 500 parallel tasks, you do dfeven equals inputdf.repartition 500. That forces it into 500 partitions, likely using round robin. Then if you know you're about to join with another data frame on customer id, And you want all data for the same customer on the same worker before the join happens. That's called co-locating data.
Right, minimizes network traffic during the join itself.
Exactly. You could use df keyed input df.repartition 200 customerid. This repartitions into 200 partitions using the hash of the customerid to decide where each record goes. And finally, if you have your final df ready to save and you want exactly 100 Parquet files, you typically do final df.repartition 100.write.parquet output path.
Perfect. Okay, so repartition is the big, potentially costly, factory-wide Lego relocation. What about the coalesce operation? That sounds like it might be a bit more localized, less disruptive.
You're absolutely right. Coalesce partitions is specifically an optimization. It's designed to reduce the number of partitions in your data frame, but crucially, in most cases, it does this without triggering that full expensive shuffle of all your data.
Ah,
It's generally a much more lightweight way to consolidate your Lego brick collections when you just have too many small boxes.
how does it manage that? How does it reduce partitions without the big shuffle? What's the trick?
The core idea behind Coalesce is that Spark tries to merge existing partitions that are already located on the same physical machine, the same executor. So instead of shuffling data all across the network, it looks at how your current partitions are spread out and tries to combine partitions that are already local to each worker to form the new, smaller set you requested.
Oh, interesting.
For example, if you have, say, 1,000 partitions spread across a 10 executor cluster, and you call Coalesce 100, Spark might try to have each executor take its roughly 100 local partitions and just combine them into about 10 new, larger partitions. It does this mostly by just reading the data locally and appending it together. No network needed, usually.
That sounds way more efficient. It avoids all that network data transfer and the heavy disk I/O from the shuffle, writes and reads we saw with repartition.
Oh, exactly. Because it minimizes data movement, Coalesce typically avoids the costly network bottleneck and the extensive disk I/O associated with the full shuffle. It's a much, much more performant operation when your only goal is to reduce the total number of partitions, maybe after a filter.
But there must be some limitations, right?
Yes.
What can't coalesce do that repartition can?
Good question. The main limitation is that Coalesce does not guarantee an even redistribution of data if your starting partitions were already unevenly sized or skewed. If some executors were holding really large partitions and others had mostly small ones, simply merging local partitions won't magically balance things out. The resulting Coalesce partitions will likely still reflect some of that initial skew.
So it doesn't fix skew.
Generally, no. That's what repartition is better for. Also, and this is crucial, you cannot use Coalesce to increase the number of partitions. It only reduces. To increase partitions, you absolutely need a shuffle, which means using repartition.
Okay, only for reducing partitions. And you mentioned coalesce can sometimes trigger a shuffle. When would that happen?
Yeah, while it's optimized to avoid it, if you ask for a really drastic reduction, like going from, say, 10,000 partitions down to just 10 and 8, Spark might, in some edge cases, find it needs to move some data between executors to achieve that extreme consolidation. In such situations, it might perform a shuffle under the hood. Also, there's an optional parameter, shuffle true, that you can explicitly pass to Coalesce. The default is false, but if you set it to true, you force it to behave like repartition and do a full shuffle, but that's rarely what you want when using Coalesce.
Got it. So coalesce is like having the builders on each workbench just tidy up by combining their own smaller boxes of Legos into fewer, larger boxes without needing a big shipment across the factory floor.
Yeah.
When would we typically use this?
A very, very common use case is right after you've performed a filter operation. Filters often significantly reduce the amount of data, but can leave you with the original large number of partitions, many of which might now be very small or even empty.
Right, lots of nearly empty boxes.
Exactly. So before you write this filtered data out, or maybe before doing a small aggregation on the smaller data set, you can use Coalesce to reduce the partition count down to something more manageable, say Coalesce 100. This usually leads to fewer, larger output files when you write, which are often much more efficient for downstream systems to read and process later. Avoids the small file problem.
And you had a code example for this too.
Yep. If you have a data frame called filter to df that came from a filter and it now has maybe thousands of small partitions, you could do coalesce df equals filtered df.coalesce 100 to reduce it down to 100 partitions. Then you'd write that out like coalesce df.write.parquet output path. You'd expect to get roughly 100 Parquet files, hopefully reasonably sized.
Perfect. All right, we've got the general Lego relocation with repartition and the local tidy up with coalesce. But what about when we have that really massive, stubbornly skewed pile of red bricks? The one that just keeps causing problems no matter how we repartition normally. That's where salting comes in, right? Sounds like a very specific fix.
Exactly. Salting is a more advanced technique. It's a direct approach specifically designed to tackle that really severe key skew head-on. It works by actually modifying the skewed keys themselves in a clever way to force a more even distribution during shuffle operations like joins or aggregations.
Modifying the keys. So in our Lego analogy, how does salting break up that enormous pile of identical red bricks?
Remember our huge pile of red bricks? They all had the same color code, so they kept getting hashed to the same overloaded bin, right?
Yep.
Salting is like taking that pile and randomly attaching a small extra identifier to each red brick before it gets sorted. Imagine adding a sticker with a random letter, say A through J, onto each red brick.
Wow.
Now, even though they're still fundamentally red bricks, when Spark looks at this new, slightly augmented color code, like read A, red B, red C, and so on, they appear as different keys to the hashing function. They're much more likely to get distributed across different bins based on these new, slightly randomized identifiers.
That's clever. You artificially make the skewed key look more diverse just for the partitioning step. How does this work in practice for joins and aggregations? They seem like different problems.
They are handled slightly differently, yeah. For joins, let's say you have a very large data frame with a severely skewed key, the fact table, maybe, and you're joining it with a smaller dimension table. The strategy involves first identifying the specific key values in the large table that are causing the skew. Let's say it's user ID 123 again.
Okay.
Then, for the records in the large table that have user ID 123, you append a random salt value, typically an integer from 0 up to some salt factor -1, say 0 to 9 if the factor is 10. You create a new salted key, like 2301239. Now, on the smaller dimension table for the row where user ID was 123, you essentially duplicate that row for each possible salt value 0 through 9 in our example, and you create the corresponding salted key for each copy, 1230, 1231, etc.
Ah, so you replicate the small table's skewed key entries.
Exactly. Then, when you perform the join, you do it on this new salted key. The effect is that the massive amount of data for user ID 123 in the large table is now spread across 10 different partitions based on the salt. And the smaller table has a matching, duplicated and salted entry waiting in each of those 10 partitions. This allows the join work for that skewed key to be processed in parallel across 10 tasks instead of just one.
That makes sense. You distribute the skewed work by modifying the key, but you need to prepare the other side of the join to match. It sounds like that duplication on the smaller table could increase its size, though.
It definitely can, yes. And that's one of the main trade-offs with salting for joins. You're essentially trading an increase in the size of the smaller table and potentially more data shuffled for that table for a huge improvement in parallelism and performance when joining with a larger skewed table. It's often worth it for severe skew.
Okay. And how does it work for aggregations? Say, counting orders per user when user ID 123 has millions of orders.
For aggregations with skewed keys, the process is usually done in 2 stages. First, just like with the join, you augment the skewed key, user ID 123, with a random salt value, 123 salt. You then perform an initial partial aggregation based on the salted key. So you'd calculate counts for 230, 123.1, etc. separately. This distributes the initial counting work across multiple tasks.
Okay, so a distributed first pass.
Right. Then, in a second stage, you take the results from that first stage, the counts for each salted key, and you aggregate those results, but this time you aggregate just by the original key after removing the salt. So you'd sum up the counts for 230 through 123.9 to get the final total count for user ID 123.
I see. An extra aggregation step.
Exactly. This 2-stage process adds an extra aggregation step to your pipeline, but it effectively avoids the massive bottleneck of a single task trying to process all the millions of records for that one super frequent key.
Okay, you had a pretty detailed PySpark code example for the join salting. Could you maybe walk us through the main parts of that again, just to see how it translates to code?
Absolutely. Let's break it down. First, you define a salt factor. Let's say salt factor equals 10. This means we'll use salt values 0 through 9. Then we assume we have a list called skewed keys list, containing the actual skewed key values we identified earlier, maybe user ID 123. Now, for the smaller data frame, let's call it small daf. We first create a tiny data frame containing just the numbers 0 to 9, our salt range.
Okay.
We then do a cross-join between small daf and this salt range data frame. This duplicates every row in small daf 10 times, once for each salt value.
Right, the replication step.
Exactly. Next, we create the salted key column. We use a conditional logic, like a when statement. If the original key in small dash key is in our skewed keys list, we concatenate the original key with the salt value from the cross join to make the salted key. If the key is not skewed, we just use the original key as the salted key. We'd probably broadcast the salt range data frame in the cross join too, since it's tiny.
Okay, that covers prepping the smaller table.
Yeah.
What about the large skewed table?
For the larger data frame, large tortorif, it's a bit simpler. We add a new column, let's call it salt. We again use conditional logic. Only for rows where the original key is in skewed keys list, we assign a random integer between 0 and salt factor 1, so 0 to 9, to this salt column. For non-skewed keys, maybe we assign none or 0.
Random salt this time.
Yes, random on the large side. After adding the salt column, we create the salted key column similarly. If the original key was skewed, concatenate it with the random salt we just generated. Otherwise, just use the original key.
And then the actual join just happens using this new salted key column that exists in both prepared data frames.
Exactly right. You perform the join between large salted and small salted using salted key as the join condition. Large salted dot join, small salted on salted key. After the join is done, you'd probably drop the temporary salt and salted key columns as they've served their purpose of distributing the workload. The key outcome, again, is that by adding that random salt to the skewed keys in the large table, those records get spread across different partitions, and the corresponding duplicated and salted records in the smaller table are waiting in those same partitions. This lets the join for the skewed key run in parallel across many more tasks, drastically cutting down the time that would have been spent bottlenecked on one or two partitions.
So yeah, it definitely adds a layer of complexity to the code. You have to manage that preparation step. But it sounds like salting can be a really powerful tool for tackling those truly persistent performance bottlenecks caused by severe skew.
Precisely. It's a strategic trade-off, right? You're either increasing the size of one table or adding an extra aggregation stage. But in situations with extreme data skew, the performance gains you get back can often far, far outweigh these costs. It can turn jobs that were crawling or even failing into much more efficient and scalable processes.
So you see, managing data in Spark is indeed a lot like orchestrating a massive Lego build. By understanding these underlying concepts like data, skew those overwhelming piles of red bricks, memory pressure, the crowded workbenches, and disk spill the overflow onto the floor, we can proactively apply strategies. Things like repartitioning the big factory-wide reorganization, coalescing that local tidy-up, and even salting the targeted fix for problem bricks, all to ensure a much smoother and more efficient assembly process overall.
Yeah, the key takeaway here, I think, is that truly effective Spark tuning goes way beyond just writing the basic code, the basic transformations. It really requires a solid understanding of these underlying mechanics, how Spark actually moves and processes data, and a keen awareness of how your specific data is being distributed and handled at that fundamental level. By diligently monitoring your Spark jobs in the UI, paying attention to those telltale signs like long tasks or disk spill, and thinking about your data in terms of how it's partitioned and shuffled, much like our Lego bricks analogy, you can diagnose those performance bottlenecks much more effectively. And then you can make informed decisions about when and how to apply these powerful optimization techniques we've discussed.
We really hope this deep dive into the inner workings of Spark has provided you with some valuable aha moments, maybe a much clearer picture of how to tackle those often challenging performance issues. What specific questions do these concepts spark for you? Are there particular scenarios in your own data pipelines, your own work, that resonate with our Lego factory analogies? We strongly encourage you to explore these ideas further, maybe revisit your own Spark jobs with this new perspective, and perhaps experiment with some of these techniques, repartitioning, coalescing, maybe even salting if you have severe skew. See how they can improve your data processing efficiency. Thanks for diving deep with us today.
And maybe just a final thought to leave you with. Consider that intimate relationship between the high-level Spark code you write, the transformations and actions you choose, like join, group B, filter, and these low-level mechanisms of data distribution, shuffling, memory management, spilling that we've talked about. Every choice you make in your Spark application code has an implicit, sometimes hidden, impact on how your data gets partitioned, shuffled, and managed in memory. Cultivating an awareness of that connection, I think, is really the crucial first step towards truly mastering Spark performance and building data pipelines that are not just functional, but robust and genuinely scalable.